Hello, I welcome you all to this another interesting screencast. The problem reads, locate the centroid Y bar of the concrete beam having the tapered cross-section shown. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. So briefly, let's talk about what centroids are. What is centroid? Centroid is the geometric center. So this geometric center, we have what is called the geometric center of a line, geometric center of an area, and like in this particular case where we're dealing with the cross-sectional area, and we also have the geometric center of a volume. Therefore, we have centroid of a line, centroid of an area. We also have centroid of a volume. And if the material or the body is homogeneous, where we are saying the material under investigation is material properties. When we say material is homogeneous, we simply mean its material properties are the same at every point throughout the body of that particular material object. And these material properties would include density, elastic, Young's modulus, Poisson's ratio, and so on. And if the material is homogeneous, then the centroid coincides with the center of mass. And if the body is acting in a medium with uniform gravitational field, therefore the centroid also coincides with the center of gravity. Right. So let's move on and start working on this problem. We have concrete beam here with a tapered cross section. Let's find Y bar. Okay. So let's choose our coordinate system. I'm going to choose our coordinate system. Let it pass through. That point. I'll move that line. I want it to be symmetrical. Okay. With this particular beam. Great. I'll pass it there like that. Okay. And then I will have another one. I want it to move. I'll bring it down very soon. Alright, something like that, but let me bring it down. Something like that. This one, I'll need to have it tilted a little bit. Just a little bit. Okay, I think I'll need to do another one. Straight one. Okay, something like this. I think this is better. Oh, great. This is better. We can go for this one now. We can go for this one. Like so. Great. So there we go. We have Y, then we have X there. Okay. So this particular section is symmetrical about the y-axis, and let's name the different parts. I'll name this part here as my part 1 of my, because I need to name these later on so that I work on them. Alright, and then I'll have two more parts, this one and this one, like this, something like this. Okay, and then I'll have these two which are right angles. Okay, these two, these are the same. This is a right angle triangle. This one is a right angle there, and this is a right angle there. Okay, all right. So this is part one. Let's call this one as part two, and then these are part three. These are the same. This right angle triangle. Great. So what do we need to do? We need to calculate the total area for everything and their local centroids. So let's start with area. Let's say area 1. What's the area for this one? The area for this one is equal to the area for this one is equal to um, 900 right, by 80, which gives us 900 by 80, it gives us a 72,000 millimeter squared. Area 2, it is a 360 times 100. 360 times 100, this gives us a 36,000 square millimeters, right? Of course. And then we have area 3. Area 3, don't forget to say there are two of them. Okay, so we are going to multiply by 2. Area 3 is 2 times half. Okay, 2 times half times 360 times we need to find this length here, using this length here, or this base, this one. Okay, what is this base? We need to find that. So we have 300 minus 100, which is 200. So 200 divided by 2 is 100. So this is also 100 millimeters. Okay, so is this one here. Okay, this is also 100 millimeters. Okay, these are the same. Let me not put a lot of information. So this is by 100. Okay, so what do we get? So we have 360 times 100 by 2 by half, just comes to 36,000 millimeter squared. All right, so let's now find the centroidal positions. Let's start with part 3, because it is at the very lowest point. So part 3, there we are. This one here, part 3, this one. So this one is x squared 3 is equal to, its whole height is 360, and half of this is 180 millimeters. All right, what about part 3? Part 3, this is a triangle, a right angle triangle. So we know that this is of course 3. I just want to move the 3 somewhere there. We know that it is going to be within this direction here. It will be somewhere here. Okay, it will be somewhere there. And we know for the triangle, right, it's always from x-axis going up, it's going to be equal to 2/3 of 360, right? Remember for the triangle. Okay, so for the triangle, x cubed 3 is equal to 2/3 from the bottom, that is of 360, and this gives us 2/3 times 360. This gives us a 240 millimeters. Okay, and then finally for part one, which is that one there, this one there. Okay, so this one is going to be equal to, that is going through half of that length there. Okay, all right, so this one is going to be equal to x cubed 1, which is equal to, so you have 360 plus half of the thickness, which is 80. Half of 80 is 40, so this gives us a 400 millimeters. So found all these details. So what we just need to do now is to draw up a table quickly and enter all these values. So we'll have one column which is part. We'll have another column. All these are y's, sorry, we are in the y's, they are not x's. I don't know what was running in my mind. All these are y's. These are y's. Okay. These are y's. Sorry about that. This is y. This is y. This is y. Okay. Yes, they are all y's. Okay. Great. So we have y cubed, and this in millimeters. Then we have what else do we have? Then we have area. It is in millimeter squared. Then we have a product of cubed and area, which is in just millimeter cubed. Okay, there we go. So draw up that table like that. Like that, like so. Great. There we go, like so. How many columns do we have here? We have just rows, rather. How many rows? 3 plus the last one, which is for summation. Great. So let's fill in this table. So we have part 1, which is just alone, then part 2 also alone, part 3 there are 2, but we've already summed up the area, and then finally we have summation. So y bar, y cubed for y1, we said is 400, and y cubed 2, where is it? This one is y cubed 2, right? This one. Okay. This one is y cubed 2, that's 180. And then we have y cubed 3, which is 240. Area 1, we have a 72,000. Area 2, area 1, 72,000. Area 2, 36,000. Area 3, there are 2 of them, but we already summed them up. They are also 36,000. The product of the two, if I extend these rows, the numbers look to be a little bit large. I extend this maybe to somewhere there. I think so. These numbers, they look low. So 400 by 72,000, what do we have? We have 28,000. Oh, I should have converted these to meters. This is too much numbers. Don't like a lot of 22,800,000. 22,800,000. Damn, this is too high. 180 by 36. This is 6,480,000 and 80,000. Then we have 240 by 36,000. This is 8,640,000. Let me check them. 400 by 72,000. We have 28,800,000. Okay, that's fine. Then we have a 180 by 36,000. 6,480,000. Then we have 240 by 36,000. We have 8,640,000. Great. Let's add up these. Let's start with the area. 72,000 plus 36,000 plus 36,000. So this gives us a 144,000, right? For sure. We add up the product of the local centroid y times a, ya. So 28,800,000. 28,800,000 plus 6,480,000 plus 8,640,000. 40,000. Okay, so we have a 43,920,000. Okay, so if I just say 28.8 plus 6.48 plus 8.64. So I have 43.92. Okay, which is okay. Right, so now finally we have y bar is going to be equal to the summation from n equal to 1, 2, and 3 of the product of y cubed times the area divided by the summation of the total area itself. Okay, the total area. And we found this already. On top we have 43,920,000 divided by 144,123. Y bar therefore is going to be equal to, so we have 43,920,123 divided by 144,000. So this gives us a 305 millimeters. A 305. Y bar therefore is equal to 305 millimeters. Okay, so let's show this in our figure. Let me just go through again. 43,920 divided by 144,305. All right. Okay, so from the bottom we are saying, if we are to use blue, from the bottom, this is our centroid there. Okay, so that is the position of our centroid, which is y bar equal to 305 millimeters. Okay, this is about it, and I hope the video is helpful. I hope the video was helpful, and if it was, this is 305. Where is it? Yes, 305. That position there, 305. Okay. Don't get worried here. I know somebody would say, why is this one 240? These were just estimations. So this value could have been very much down there. It could have been down there. So somebody could get worried and say, but why is it there? It could have been down here. These were just estimations. Okay, for those points. All right, you don't have to get worried about that. This one could have been here somewhere there. Okay, but nothing changes. It's not affected by anything. All right, you don't have to get worried about that. So this is the final solution. This is the final solution for this particular problem. That is the centroid Y bar of the concrete beam having a tapered cross section. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing, liking my channel. Bye bye, and see you in my next screencast.